Hello, welcome to m253, Calculus 3 here at Cañada College. My name is Lapuz, and we're doing checkpoints from section 6.7, the section on Stokes' theorem. This is checkpoint 6.61. They want us to verify Stokes' theorem is true for the vector field f of x, y, z is equal to y, comma x, comma negative z, in the surface S, where S is the upwardly oriented portion of the graph. Z is equal to x squared times y over a triangle on the xy plane with vertices 0, 0, comma 2, 0, comma 0, 2. All right, well, let's take a look at the xy plane first. I guess that's a good place to start. And, oops, we have the highlighter going on here. Let's use a regular pen. We have 0, 0, 2, 0, and 0, 2. So on the xy plane, this is what we have. And if z is going towards you, as our standard z going up out of the page on the xy plane, from the xy plane, we have the orientation going in the counterclockwise direction. So imagine the arrows going up, and then your rotation is in the counterclockwise direction using your right hand rule. All right. So let's write down Stokes' theorem. Stokes' theorem says that we are trading a flux of the curl. So here's the curl, and this is a flux double integral over a surface dotted with d capital S, where ds capital S is the normal normal vector, and this is a normal going upward. And this is going to get replaced, or can be replaced, with a line integral, a single integral, over the boundary of S, and we'll use this notation for the boundary of S. And we're looking at not the derivative, or not the curl of f, but just the original f vector dotted with r, and r is like the tangent circulation. Okay. All right, what do we have here? We have a flux of the curl versus a line integral. And when they say verify, they usually mean do both. Let's do both. All right, let's start with the line integral. That's the more difficult one. And for the line integral, your delta S, sometimes just simplified as the curve C, is going to be actually C1, C2, C3, a union of three curves. Actually, this is not the C that we want. So this is not the boundary that we want. So let me just change the notation just a tad bit and call it C hat. And C hats, these hats are two-dimensional, whereas the actual C that we're looking for has to be three-dimensional. But I think it's a good place to start with two-dimensional, because we can parameterize these C1, C2, C3 hats, and then we can take it to the third dimension by adding the Z component to it. So in terms of the hats, remember the hats are in 2D, 2 dimensions. And again, we'll kick that up to the third dimension after we figure out the X and Y components of the 2 dimensions. And remember that they are going to be projected onto this surface. So once we get the X and Y components of your C1, C2, C3 hats, we'll put the X and Y components into this function to get our Z components. and then that would be your regular C1, C2, and C3. Okay, let us figure out what C1 is. C1 is a line segment going from 0, 0 to 2, 0. And so there's no movement in the y component. And then we can put t in for x and let t go from 0 to 2. But I think it's better to actually scale it in the parameterization. So whenever we do an equation of a line, we're always going to go from 0 to 1. So if this is 2t, and then when t is equal to 0, this is 0, 0. When t is equal to 1, this is 2, 0. And that's exactly where you want to be. And let's just put t going from 0 to 1 for all line parameterizations. Okay, so that's C1. Again, we're still in 2 dimensions, so we'll kick it up to 3 dimensions after we figure out all the components. C2, in the x component, the x is going to go from essentially from 2, 0 to 0, 2. So your x component is going to shrink down to the negative. So if you put 2 minus 2t, that'll bring it back down to 0. So when t is equal to 0, um, this is 2 minus 0, so this is going to be 2. When t is equal to 1, this is going to be 2 minus 2, which is 0. And so that's you want the movement for the x that way. And the y, meanwhile, goes from 0 to 2, so again, we'll just put 2t. There is a formula to find an equation for a line segment, if you remember, if you want to go from the point x1, oops, if you want to go from x1, y1 to x2, y2, a line segment connecting these 2 points, you would go with the starting point x2 minus, or x2 comma y2 plus t times the direction vector, and the direction is going to be the difference between them, head minus tail. So it's going to be the x2 minus x1 comma y2 minus y1. And the parameterization for this will be 0 to 1. Okay, so that's kind of like what I'm using, but I'm kind of abbreviating that and doing it rather quickly. And that's how I'm coming up with these parameterizations. All right, C3 now is going to go from no movement in the x direction, so that's 0 in the x. It's always going to be 0. And then the y goes from 2 to 0, so again, it's going to be 2 minus 2t. And I think we call these things hats because the hats are in 2 dimensions, and we're about ready to take this up to 3 dimensions. All right, when we bring it up to 3D, the actual 3D curve, we'll call it just a regular C1, and this will have the 2t comma 0, and now we're going to put the x component into the function. So x is equal to 2t quantity squared, and the y, which is 0. Oops. So that's essentially going to knock out this third component of this parameterization. So your R1 is going to be 2t comma 0 comma 0. And again, t goes from 0 to 1. So if we parameterize this, we'll see this piece of the curve that's on the surface. And it looks like along the x-axis, the surface is just going to ride along a zero height. All right, C2, again, it's going to be the same, 2 minus 2t for the x, 2t for the y, and then now we'll plug it into the z. And so the z will have a 2 minus 2t squared times 2t for your y. Now we can simplify that. I'll hold off on simplifying it. Now I'm going to, just for the sake of not making any algebra mistakes, I think I will let my calculator do the work for me. Well, I suppose we will need to take the derivative of this because we're doing the line integral and the dr is the derivative. So I guess we'll need to simplify it after all. So r2 of t will be equal to 2 minus 2t comma 2t. Now let's FOIL this out. This is going to be 4 minus 2 times 2 is 4 times 2 is 8. And then negative 2t squared is going to be positive 4t squared. And then we're going to multiply this by 2t. So this becomes an 8t minus 16t squared plus 8t cubed. Okay, it's getting a little bit messy, but it's still a polynomial. So I think we're still okay. All right, C3. This third one is going to be a 0 for the x, a 2 minus 2t for the y. And so when we put that into the function, 0 for the x, and it doesn't matter what happens next because the whole thing is going to be 0. So your R3 of t will be 0, 2 minus 2t, and 0. All right. So again, for this line integral on the right-hand side, since the line is in 3 pieces, your closed curve is in your closed piecewise continuous curve is in 3 pieces. We're going to have to do 3 integrals. Okay. Now let us take the derivative of each one because we will again need to dot it with r or f of r. So r1 prime of t is going to be 2 comma 0 comma 0. R2 prime of t is going to be negative 2 comma negative 2 comma. Now this polynomial is going to be an 8 minus 32t plus 24t squared. That's your derivative. And then the last one, R3 prime, is going to be 0, negative 2 comma 0. All right. Now the other thing that we'll need is we'll need to figure out the line integral. We need to evaluate the vector field using each parameterization. So let's do that. F of R1 of t uses this R1 of t function, and then we're going to put the x is equal to 2t, y is equal to 0, and z is equal to 0 into the vector field. So that will give us y is equal to 0, x is equal to 2t, and z is equal to, well, that's 0 again, so that's going to be 0. And when we integrate, we're going to dot these two and then integrate from 0 to 1. All right, now let's figure out how this is going to look like. F of R2t, and we're using this, remember, R2 of t into the f function. So the f vector field gives a y component first, and the y component is 2t. It gives the x component second. That's 2 minus 2t, and then it gives a negative of the z component. So that's 8t minus 16t squared plus 8t cubed. And we're going to dot it with this which does not look pretty. All right, the last one, R3. So f of R3 of t is going to equal to, we're going to put y first. So it's 2 minus 2t comma the x second, and then the z, negative z last, but that's going to be 0 anyways. All right. I want to focus on the first and the last one because they're going to end up being quite easy, simpler maybe. And so your line integral for the first one, line integral of C1 f dotted dr, it will equal to the integral from 0 to 1 of f of r of t dotted with r prime of t dt, and this is the integral from 0 to 1 of the dot product of these two, so that's 0, 2 times 0 is 0, 0 times 2t is 0, and 0 times 0 is 0. So that turns out to be 0. We're done with that. Now let's figure the last one. 0 to 1 again of the dot product. So that's going to be 0 times 2 minus 2t, so that's going to be 0. Negative 2 times 0 is 0, and 0 times 0 is 0 dt. So the integral for C2 is also going to be equal to 0. All right, now let's do this one. So this one is not going to look very nice. In fact, it's going to be tedious with the algebra. So I'm going to actually take a shortcut, but let me write this out at least. C2 of f dotted with dr is going to be the integral from 0 to 1 of this thing. Let's write it out. 2t comma 2 minus 2t comma negative 8t minus 16t squared plus 8t cubed dotted with r prime, which is minus 2 comma, this is positive 2, I think, minus 2 comma positive 2 comma 8t minus 16t squared plus 8t cubed dt. All right, that's our integral. This is not difficult, but it is a little tedious, and you have to be meticulous with your algebra. But I'm going to do a little legwork here and just ask Wolfram Alpha to compute it for me. And what's neat about this is that Wolfram Alpha can use the dot, literal dot, as the dot product. And they normally use curly braces for vectors. So we have 2t comma 2 minus 2t comma negative parentheses 8t minus 16t squared plus 8t cubed, close parentheses. So that's the first vector, that's f of r of t, and then we have a negative 2 comma 2 comma 8t. Uh-oh, that doesn't look right. The derivative should be the derivative should be 8 minus 32t plus 24t squared. All right, we got that fixed over here. So now let's take a look at Wolfram and put the appropriate value. So that was 8 minus 32t plus 24t squared. And now we're going to evaluate this for t going from 0 to 1. Okay, let's see how it goes. All that, and we get 0. So we have a 0 contribution from the first curve, a 0 contribution from the third curve, and now we see that a 0 contribution for the second curve as well. So it looks like all in all, your line integral is going to be the integral of the boundary of your surface of f dotted with dr is equal to 0 for the first, 0 for the second, 0 for the third. So that's equal to 0. No contribution at all. All right. So that's the right-hand side of the Stokes theorem as written here. Now let's take a look at the flux of the curl. So flux of curl, and that's the double integral over the original surface. And that would be the curl and then into the flux formula. So in this case, we would have to parameterize the surface and get the value for that. Now, before we parameterize the surface, let's figure out the curl of f. Curl of f. Remember that f was equal to y comma x comma negative z. So the curl, or at least the calculations for the curl, can be seen as like the matrix ijk, partial with respect to x, partial with respect to y, partial with respect to z. That's your del operator, and then y, x, negative z, right? y, x, negative z. Okay, so that looks good. Let's compute this. In the I direction, it's going to be the derivative of negative z with respect to y, that's 0. Derivative of x with respect to z, that's also 0. The j term is going to be negative. The derivative of negative z with respect to x is 0. The derivative of y with respect to z is also 0. And then now in the k component, the derivative of x with respect to x is 1 minus the derivative of y with respect to y is 1. Okay, there we go. The curl is actually equal to 0. And so if we take the surface integral of that, or the flux integral of that, we're going to get 0. So we don't actually need to parameterize the surface anymore because this whole thing is 0 anyways. Okay, there we go. It is now verified. Now we got 0 using the flux and 0 using the line integral. So we're done with this problem. It's verified, but I do want to show some pictures and the way the parameterizations work. Let's start with the surface itself. I have most of the stuff done here in CalcPlot 3D. So this is a surface, x squared times y, and they want us to focus specifically on this triangle under this triangle. So let's clear out the surface for a moment. And this is the triangle that we're looking at on the XY plane. Now, I parameterize this using a parametric surface. And so we don't need to worry about how this was obtained. Let's just say that that surface is given by when x is equal to 2v and y is equal to u times 2 minus 2v. And right now z is equal to 0, so this is all happening on the xy plane. Now if we use that technique where we take our function, which is x squared times y, and then we put in the x squared, the x value here, so the x value of our parameterization is 2v, and the y value of our parameterization is u times 2 minus 2v. And then if we put that into the function, x squared times y, then we can see this surface, or this piece of the surface, and still right above the triangle that we're talking about. And just to confirm that that's actually on the surface, we can redraw that surface again and see that it's actually on that surface. All right, so this is the piece of the surface that we're looking at. With an upward orientation, we can do the parameterizations of those lines in a second, but this is the view of the surface. All right, now let's focus on the parameterizations. The parameterizations are happening this way. Along the x from 0, 0 to 2, 0, you have this, and it might be better if we restrict our view to 2 dimensions, and it might also be better if we get rid of the axis for a moment. So let's not show the axis for now, and this is well, we'll put the axis back and we'll take it out later. But you can see the first parameterization, the second parameterization, and the third parameterization. Let's take out the axis now so we can see that triangle. So this is a triangle. The arrows show the orientation of your curves. Okay. At the moment, we are restricted to 2 dimensions, and so if we take a look at not restricting this to 2 dimensions anymore, this is what we're seeing, and this is covering, if we put this back to 0, the triangle that we're looking at, this is the covering the triangle. Now we want to remember that we want to see this up along the surface. So we want to see, it looks like the parameterization that's going along the axis stays at 0, which is what we saw, but now this blue parameterization needs to go up on the surface. And this is where we look at the x component and the y component, and we put it into the function. And remember, the function is x squared times y, and the x is going to be 2 minus 2t, and then the y is just going to be 2t. So if we see that again, we can see now it is up along the surface. All right. And so here is the surface and the boundary of the surface. We can focus just on the boundary of the surface. If we take the surface out, this is how it would look like in 2 dimensions. You see that it's just really the form of a triangle, but in 3 dimensions, you see that that third curve actually goes up. And now let's put the axes back. So this is actually what we're looking for as the boundary of the surface. And if we want to include the surface as well, And this is the surface and the boundary of the surface put together. All right, so that's the geometric point of view. We haven't even drawn the vector field, but if we draw the vector field here, um, and this is where it might start getting confusing, but the vector field was y comma x comma negative z, and let's fill up the whole vector space with the vectors, and it would go like this. So it's not easy to see what's happening, and it's not easy to guess what your final outcome would be, but apparently uh, the flux of the curl here is going to be 0. I guess if we're looking at the vector field itself, we're looking at the line integral of the vector field, so uh, it would be focusing on what's happening along the surface, along the curves, not the surface. Okay, so that's the geometric viewpoint of this problem, um, but the actual Stokes theorem analysis is kind of laid out here. Okay, I hope that helps. I know that's a lot, but it's what we need to do for these different things. Normally, Stokes theorem will ask you to just do one side or the other, and a lot of times one side is going to be easier. Sometimes it's going to be the line integral side, sometimes it's going to be the flux of the curl side. So it really just depends on the problem on which side is going to be easier. Okay, good luck.